Hi everyone, my name's Daniel Holden, and today I'm going to be talking to you about a bunch of different interesting things: machine learning, physics simulation, Kolmogorov complexity, and squishy bunnies. So the kind of end goal of this talk is to show you how we got from this to this. So we started with a simulation which is running at about half a frame per second, and we ended up with a simulation which is running at almost 3,000 frames per second. And to do this, we use some machine learning techniques. And today I want to kind of talk you through what our different thoughts were for this project and kind of the journey we went through. So first, a little bit of background. So I've been working on doing research in kind of games, graphics, and animation for almost 7 years now. And what I'm really interested in at the moment is how can we use machine learning to help game development scale. So games are getting bigger, they're getting more complex, they're getting more expensive, they're getting harder to build, and how can we use machine learning to make this easier? So I think probably all of you have seen something like this. So it's a budget sheet. It says how much computation time and how much memory you're allowed for all the different systems in the game. And actually contains another secret column. So here we have the quality budget, and this one there's no kind of numerical value to. It's more like you go to your lead, or you go to the designer or the producer, you show them the system, and there's like a kind of yes/no switch which says, do you reach the quality budget or not? And we were thinking about these budget sheets and kind of asked ourselves two questions. One is, what if these first two columns didn't exist? So what if we had no limit on memory or computation time? What might we do to try and achieve the highest possible quality? So what sort of techniques could we take from different industries, like the film industry, elsewhere? And secondly, what if we could specify our memory and computation budget and somehow automatically test it against some quality budget? Without getting someone else involved. So what if we had these sort of sliders we could slide and see, okay, with this system, we're reaching the memory budget and we're reaching the quality budget, but maybe not the performance budget. If we slide down the computation, maybe the quality goes down, these sorts of things. And more concretely, like how could this work? How could we build systems like this? So basically what we want is we want adjustable systems. So we want systems where we can adjust the memory usage, we can adjust the computation time, and as a result, the quality changes. So lots of our systems in games are already like this. For example, we have physics simulations where you can dial down the number of iterations or the number of time steps, or we have rendering problems where we can use a simpler, cheaper rendering algorithm to try and achieve the same effect, so the quality is worse. But is there kind of a more general way of encompassing this idea? So here's kind of maybe the thing which will be surprising to some of you, which is that all mathematical functions have this property. So actually, all systems could be given this property in theory. So that's what I'm going to talk about today. How can we build these adjustable systems and how do they work? So first, a little kind of example. Let's say we have a very simple function like the sine function. We can think of different implementations of this sine function. So we can think of them in terms of their memory usage and computation time. For example, just a normal computation of sine, like you might be used to, it doesn't use any memory. It's kind of just it's maybe even implemented in the hardware, so it's just like a single call. And we think of this like the direct computation of the function. Another option is to use a lookup table. So what we could do is we could pre-compute every single value of this function, so every single output for every single input, and we could store this in a big table. And then at runtime, when we want to know the value, we just jump to the position in this table we need and we get the value instantly. So for a function like sine, this might seem odd, but you can imagine for a very complicated or expensive to compute function, this can be a lot faster because all we need to do is jump directly to the answer. The problem, of course, is that now, one, we have to pre-compute all these values, and two, we have to store them all in this big table. So in a way, you can think of this like trading memory for computation time. So here, it's using lots of memory in exchange for very fast computation time. We can also think of some things which are in the middle. So, for example, we can do cached computation where for inputs we've already seen, we compute it and then we store that in a lookup table. So here we can see that if we've already computed the answer for a particular input, we can get it straight away. And the exchange is that now we have to store all these answers we've already computed in a table. So it's somewhere kind of in between in terms of computational cost and memory usage. Another option is function approximation. So here what we can do is we can find a function which gives a similar result but is less expensive to compute. And it might be unintuitive where the memory in this comes in. Actually, for example, this is an approximation of the sine function I found. And here we have these constant values. So these are actually the memory, these kind of additional constant values. And if you extend this function approximation to more complex functions with more inputs and more outputs, you'll see the number of these constant values will grow, and actually you can end up using a lot of memory. So that gives you a sense of how we can actually make different programs on these axes. So what other sort of programs can exist on these axes? Because if we can find these generic programs which can exist on these axes, it's very powerful because it doesn't matter which system we're modeling. So there's actually a huge class of these programs which we often ignore in game development. And these are basically machine learning algorithms. So the idea is that we pre-compute this function offline for many different input values. And we use this as a data set to train a machine learning algorithm. So we have our pairs of inputs and outputs. And after this, we can exploit the fact that different machine learning algorithms have different computation and memory characteristics, and this can put us in different places on this graph. There's actually some nice additional advantages to this approach too. So, for example, we can use a more expensive version of this function when we compute it offline. So if we want to achieve the maximum quality, we can use a very expensive version of this function, because if we're computing it offline, it doesn't matter how long it takes, up to a point. We can also use our prediction accuracy as a proxy for our quality. So let's say we train a machine learning algorithm and it is approximating this function to some degree. If we assume we have the perfect kind of high quality function, we can see how well we're approximating it and use this to measure our sort of quality. So actually, if we look at machine learning, we have all sorts of programs on these axes. So we have linear regression, polynomial regression, nearest neighbor regression, lots and lots of different algorithms. And all of them have interesting properties. But today we're going to look at just neural networks. So these have a particularly interesting property for our task, and that's what we're going to find out. So if we look at a neural network, most of you have probably seen a diagram like this. What is the characteristics of computation time and memory usage? So at the end of the day, it all comes down to the number of weights. So our computation time is actually proportional to the number of weights we have in the network. And this is also the same as the memory usage. So the memory usage is the same as the number of weights we have. And the memory usage is proportional to the accuracy. So if we have a bigger neural network, we're going to get a more accurate result. And finally, the accuracy itself is proportional to the complexity of the function we're trying to model. So if we have a very, very simple function we're modeling with a neural network, we're going to be able to get very high accuracy with not many weights. On the other hand, if we have something very, very complex we want to produce with the neural network, we're going to need a lot of weights. So we can think about neural networks as lying on the sort of diagonal of this graph, where the diagonal is this kind of complexity. So neural networks are going to slide up and down on this diagonal depending on the complexity of the function we're modeling. If we have a very, very complex function, the memory usage and computation time is going to be very bad, whereas if we have a very simple one, we're going to hit this sort of sweet spot where computation is very fast and we don't use very much memory. So when complexity is low, we're going to hit this sweet spot. That's cool. But what actually is complexity in this case? And can we actually measure it? So can we have a function or something like that, a system in a game? Can we measure its complexity to get an idea of how well neural networks are going to do? So that's where Kolmogorov complexity comes in. So this is a kind of theoretical, abstract measure of complexity, and theoretically it's defined as this. It's the length of the smallest program which can produce the given outputs for the provided inputs. So that sounds kind of odd because it's like the length of a program. But this is the definition of this complexity, and we'll see how this makes sense. And there's a couple of kind of caveats. The first is that it doesn't actually matter which programming language we use in this case. There's some proof which shows that it's invariant to whichever program we use up to some constant. And the second thing is that we're not allowed to open files or communicate externally in any way. All the data we need has to be embedded in the source code of the program. So let's have a look at some examples. So here we have a string, it's just A and B repeated. And this is not a very complex string. The function which produces this string is not very complex. We can write it like this. It's just a simple loop which prints A and B. On the other hand, if we have a string which is all these different random letters, there might be no program which can compute this easily. The best thing we can do is just print it out verbatim. So we can see already there's sort of something interesting here, which is that if we have a function which is less complex, it means we're doing more computation. Whereas if we have a function which is more complex, we're doing memorization instead. So we're just memorizing the output. So as a little aside, why does the programming language not matter? Because we can imagine we have this string A, B, A, B, A, B, and we have a programming language we built ourselves where the function for producing this string is some very long, pointless function name. On the other hand, we could have this random string, and we could have a built-in function which prints this out with a very short name. So it seems a bit odd that it doesn't matter about the programming language. So is this really like less complex? So the kind of proof or the trick here is to say that we need to add the compiler to the length of the program. So all these built-in functions, everything like that, it needs to be added to the length of the program. So now if we have any long random string, it's going to need to appear in the source code of the compiler. So up to some point when we have a very long kind of random thing, it's going to result in a very complex compiler which has to memorize it. That's just a little aside. So let's have a look at some more examples. Let's say we have this image here of this bark. So do you think there is a simple program which can generate this image? So not really, right? What we have to do is actually memorize this kind of texture and print it out verbatim. So there is some sort of patterns in the bark. Maybe there's something we can do. But if we really want to produce this image, we're going to have to write a complex program which memorizes a lot of things. And what about an image like this? So this is much less complex, so I think we can all see that we can imagine a program with simple rules which can generate this image. So yeah, this one has simple rules that can generate it, and we can see that natural data kind of textures and that sort of stuff, it often requires memorization. Let's look at a couple more examples. So what about this image, this animation? So I think most of you have guessed this is not complex because this is a fractal, and we know that programs which generate fractals are generally pretty short. So this is kind of an edge case where we have something that visually it looks complex, but actually there's very simple rules that can generate it. So that's interesting. And what about this one? So this is a trick question. So if this video of noise is truly random, it's truly a random noise, then it's kind of the maximally complex program. There's no program we can make which does any better than just printing it out verbatim. On the other hand, if it's pseudo-random noise from a pseudo-random number generator, we know it's not that complex because pseudo-random number generators are not very complex programs. So here we see that, like, even though it seems intuitive, there are these edge cases which can confuse us. And in the kind of pathological case of this noise, it's actually completely impossible to tell whether this is a complex thing or not a complex thing. So I think at the high level, with all the or not a complex thing. So I think at the high level, with all the edge cases and everything like that, a sin is required by a function, or maybe even more how much information exists within a function. So these are all very abstract conceptual things, but how does this actually work in the real world? Like, can we use this idea of complexity with a real game system like the ones we build in our games? So let's look at our budget sheet and we can think of some different candidates. So one interesting candidate is physics simulations. So why is this? Well, they're a large isolated game system, so they have some sort of input and output which we can isolate. They can be computed offline and at a higher quality, so we know we can get really high quality training data. And they don't do any memorization. So usually these systems, they memorize a bit of state, they cache a bit of stuff, but they don't memorize anything aggressively. So it seems like a good candidate where we can try and add some memorization to get some more performance. So how are we going to set this up? Well, we have our physics simulation. We can think of our physics update being the mathematical function. So here we have something like the vertex positions and the collision geometry as input, and the next frame's vertex positions are going to be the output. And this is going to be our mathematical function. So the first thing we need to do is we need to convert the inputs and outputs to these big vectors. So it really needs to be a mathematical function that takes a big list of numbers as input and outputs a big list of numbers. So we can take all the vertex positions and just flatten it into one big vector. And we can do the same for all the objects in the world which it might collide with. We can put all their properties, like their position, their radius, etc., into one big list. And now now we really have a mathematical function, which takes a list of numbers and outputs another list of numbers. So if we want to evaluate the complexity of this function, we need to get some inputs and outputs. So what we can do is we can just evaluate this physics function over multiple different frames, and we can concatenate all the different vertex positions into one big matrix. So once we have this matrix, we can ask what the complexity is. First, let's just kind of look at a visual example. So let's say you saw this swinging ball and sheet. Would you think that this is complex or not? And forget about the edge cases for now. Assume you were given this data, the vertex positions of this cloth, and you had to build a function to approximate it. Do you think it would be a complex function? So maybe surprisingly, I would argue this is not a very complex function. And the reason is this. The movement of this cloth can almost entirely be described by one parameter, which is the swing phase of this ball. So we can sort of encode all of the movement of this cloth in just one parameter in a way. What about something like this? So this is much more complex. Here we have all sorts of chaotic movements and fine folds and collisions. There's a lot of detail going into this simulation. So here it's clear we can't just take one or two parameters and fudge things around to try and produce this sort of output. So how are we going to actually compute the complexity of this simulation? So what we want is something which will kind of tell us for each of these cases how complex it is. Actually, there's no way to compute the true complexity, but we can use an algorithm called principal component analysis, or PCA, to get an approximation of this. And this is going to approximately tell us how complex this data is. So when we apply PCA to physics data, we get what are called the modes or axes of deformation. And the number of these modes which are required to reconstruct the original data is what tells us the complexity. So I'll show you what that means. So here I'm visualizing the different modes of deformation for this ball and sheet example. So we can see some modes correspond to the sheet swinging, some to it twisting or deforming in other different ways. So basically, we want to reconstruct the position of the cloth as a sum of these modes. So we give each of these modes a weight and we add it together. This is going to represent our cloth state. So sometimes modes are called bases. So if you see bases, or I say bases, just think modes. And here we can see different numbers of modes applied to some cloth. So we can see here that if we reduce it down to just 64 modes, there's some loss in detail, but we still have roughly the kind of rough details preserved. So here we can see that actually, if we have a high-resolution cloth, this input to this physics system, if it's 10,000 dimensional vector, 10,000 numbers, we can reduce it down to just 256 numbers, and we still capture pretty well the details of the cloth. So this tells us that physics simulation is almost always less complex than it appears. And if we want to make it even simpler, we can just keep reducing the number of modes and we get like a rough approximation. So there's actually some good theoretical reasons why physics simulation is kind of less complex than it appears in this case. Some good theoretical reasons why physics simulation is kind of less complex than it appears in this case. All right, so let's go back to our and physics simulation. So here we can see that if our modes are low, we're going to hit this sweet spot, basically. So here we can replace complexity with modes. Given a small number of PCA modes, neural networks should perform well. All right, so that was all kind of theory. So let's actually do this. Let's see what happens. So we're going to do two different applications. One is going to be on some cloth simulation, like I've shown. Another is going to be on soft body deformation. So we can put the two in the same package because at the end of the day, the input and output is just the vertex positions. So first we need to gather some training data. So we need to have a physics function which we can evaluate offline. So it's natural to ask, can we actually use the in-game physics simulation we use now for cloth? So here's an example from Origins. So we can see it's looking pretty nice. But if you look closely, you'll notice that there's actually self-intersections of the cloth, and there's other kind of problems which appear as well if we're looking for really high-quality simulation. So basically, the problem is it's too highly optimized for real time. There's no self-collisions. We have no cloth-on-mesh collisions in our cloth sim. The stiffness also changes with the DT or the number of iterations. So we need to find a different way to get data. So one thing we looked at was getting data offline using Myers encloth. So one problem we had is stiff materials. So we used the kind of presets, the preset material settings. And as you can see, the cloth actually appears a lot stiffer than what we're used to in games. So we weren't really sure exactly why this was. Maybe it's just a difference in perception between games and physics sims which are geared towards very realistic simulation, or maybe it was something else that was set up incorrectly. Second problem was the simulation can break very easily. So here we have an animation where the character puts his elbow through the floor, and here this kind of broke the cloth. And when it gets stuck in these bad states, it tends to not return, and all the data from then on is broken. Finally, we had some self-intersections. So here in this animation, the character would intersect his thigh with his hand, and this would pinch this skirt and cause it to explode. So here we just cut off the guy's arms, which may be a bit extreme, but in this case it solved the problem because we don't anymore have collisions between the arms of the character and the cloth. The final problem is that it takes a very long time. So this is the real-time recording of how the simulation looks. So it's one frame every 2 seconds. If we look at some of our data sets here, some of them took several days to generate. So that's really long. I think it makes sense to parallelize this in future. So once we have our data set, we need to apply PCA and extract these PCA modes. So here we get all of our vertex positions, let's call them X. We'll stack them into a vector for every frame. So this is for every different frame. And we can put all these frames together into one big matrix X. And then we can apply PCA. So this U is the PCA matrix, and we can extract the PCA modes. So now we get those kind of 256 or however many modes we've chosen, numbers per frame representing our cloth state. We also have the external objects in the world, like this ball which is colliding with the bunny, or the pose of the character. So these are our external collision objects. And we're also going to apply PCA to these, so we're going to compress these and find some new lower dimensional representation of these. And now what we're going to do is we're going to train a neural network to predict something like a correction from the extrapolated PCA modes and the PCA modes in the previous frame. So it looks something like this. Here we have the PCA modes in the previous frame. Here we have some extrapolated version of the PCA modes. So basically we're adding like the velocity of the PCA modes multiplied by the time step. And here we have the modes in the next frame. And here we have the compressed collision objects, so everything in the external world. And this is our neural network function. So we're going to train our neural network to kind of add this small correction, which is going to predict the state in the next frame. So we can actually train our system like this, which is going to predict the state in the next frame. So we can actually train our system like this. We can just kind of shuffle around a few of these terms, and so the cloth will quickly explode and it'll go into states where it's never been seen in the training data, and things will get even worse. So what we actually need to do is predict multiple frames during training. So you can think about it something like this. Say we have some ground truth kind of trajectory of the state of the cloth. We might start at this point, so we already have some error. First, we're going to extrapolate forward what we think the state is going to be in the next frame. And then we ask the network to do this correction, so to pull it back onto the ground truth. So we do this. And then at the next frame, we got a new extrapolation. And it's going to go further off the path again. And we ask the network to correct it again. And it's going to have to make an even bigger correction this time if it has to fix any errors in the extrapolation. And so you can see this slowly becomes unstable and the system is unable to follow the trajectory. So on the other hand, if we don't try and ask the network to correct completely every frame, but actually just ask it to get a good result over a whole window, then we can get much better results. So let's do the same. Here we start with our state of the cloth. We extrapolate forward. Rather than getting the network to completely correct the system, we just ask it to do a small correction. And now when we extrapolate forward the next frame, we're already going to be much closer to the state of the cloth. So here we ask for a small prediction again. And in this way, our tracking can become much more stable, and the whole prediction system corrects for itself and goes back to these trajectories. So if we try and predict a window of frames, we get much more stable result. So here's some results. So here we've trained our system on this ball and sheet example. So I think already you would be hard pressed to tell that there was no physics simulation happening in this system at all, and everything is going on through machine learning. Here's another example. This is sort of like 4 pins on the side of a cloth. So again, I think it would be very hard to distinguish between this and a true simulation. One interesting thing is we can add any sort of external variables we want. So here we can add some sort of wind speed and wind direction to this state. And the network here will learn what changes in this will do to this flag. So here I'm going to show a comparison between the ground truth, that is our training data, and a prediction of our method. So this is from some validation set, so it's a motion which the system was not trained on. So here we can see it does actually lose a fair amount of details, but it does a pretty good job at preserving the overall kind of shape and features of this cape. And of course, it's much, much faster. Here's another example. So here we're interacting with a deformable object. And in this case, it's actually a massive, massive improvement because these sorts of deformable objects are extremely expensive to simulate, as you saw. Here's a slightly more complex example. So here we have the interaction object is a teapot, and the thing being interacted with is this dragon. So here the neural network needs to learn kind of everything. It needs to learn about the shape of this teapot. It needs to learn about the shape of this dragon mesh, and it needs to learn about how these two things interact. So you can see here that it does a pretty nice job of modeling these collisions, even though the mesh about how these two things interact. So you can see here that it does a pretty nice job of modeling these collisions, even though the meshes are very complicated. Doing the simulation, it no longer depends on the vertex count. It only depends on the number of modes we use. So for a neural network, it is kind of the square of the number of modes we use. Of course, at rendering time, we still need to pay for how many vertices we use. So the GPU cost is the number of modes times the number of vertices. And you can see that if we use just 64 modes, then the evaluation time is extremely fast. So it just takes around 35 microseconds. So this is very, very fast. On the other hand, if we use 256 modes, the computation time starts to grow, and we sort of start to hit what is roughly the budget for a kind of AAA character update. So we're still within game speeds, but as we add more and more details, we start to push the limits. Of course, it's still thousands of times faster than the training data, but the training data was very slow with very high quality settings. So here's a comparison between the different number of bases you use. So you can see here that if you reduce just down to 64 bases, you get a very, very rough approximation of the cloth. But this might be interesting for like levels of detail or different characters or physics simulations which are far away. They don't require the same amount of computation. So here we really do have this kind of sliding scale of computation and memory usage. So what happens if the input is really far from anything we've trained on? So basically it can be unpredictable. In our cases, most of what we found was that it does something fairly sensible-ish. And we can also kind of clip the inputs, so we can clip the kind of maximum speed of the interaction or the position of the interaction. And this can prevent this extrapolation a bit. All right, so in conclusion, well, we can do this, so we can simulate thousands of squishy bunnies. But perhaps more interestingly, this sort of budget sheet we talked about at the beginning, it is possible. It is possible to build systems like this in a generic way. However, getting the training data is not always easy. So in particular, in the case of physics simulation, there's lots of difficulties you need to overcome. More complex systems get difficult to improve upon. So we saw there was this sweet spot with not very complex systems where we can get really incredible performance. So it's important to identify how complex you think the system is going to be, or try and get some sense of that when you apply these approximations. And the accuracy is often a poor proxy for quality. So if we remember when we trained our neural network on a frame-by-frame basis, even though the loss of the training went very low, when we actually ran our system, it was hugely unstable. So in this case, the accuracy was a very poor evaluation of the quality, but maybe we can tweak things and try and get a better approximation. I think if you're going to have one takeaway from this talk, it would be don't dismiss expensive techniques from the start. So this idea where we cut out this part of the table with the memory and computation budget, I think this is very valuable. And it's useful at least as a reference or a kind of goal for what you're trying to achieve. So having the kind of brute force, expensive, but really, really high quality simulation or whatever system you have is really valuable. And if you have this data, if you have this really high quality solution, it also opens up the potential of exploiting this idea of memorization versus computation. So if you have the kind of perfect solution, maybe you can just memorize it and play it back. Maybe you can do some sort of function approximation. you have many options when you have this really high quality ground truth data. So that's everything. Thank you very much.